in section 14.5, we thankfully move away from all of the quantitative analysis of reaction kinetics. And we're going to talk a lot more qualitatively until the end of the chapter, which I know some of you will like. So let's consider a simple chemical reaction. NO2 plus CO goes to CO2 plus NO. And it's certainly easy to imagine this reaction proceeding in a single step. The carbon monoxide and the nitrogen dioxide collide in the proper orientation for the oxygen to hop from one molecule to the other. But even though that kind of makes sense, and it's certainly possible, is that really how it happens? And the reality is that many reactions will take place in multiple steps, sometimes in surprising ways. And those two or more distinct steps are going to have observable, measurable effects on things like the reaction rate. And so the details about how a reaction proceeds is called the reaction mechanism. And each of those steps can be broken down into either a spontaneous decomposition of one large molecule into two smaller ones, or the collision and reaction of two smaller molecules to form one or more new products. So those individual interactions are called elementary steps. And elementary steps cannot be broken down any further. They are an actual description of the types of encounters and processes that occur on the microscopic level and on the nanosecond time scale. So reaction mechanisms are made up of one or more elementary steps. And here's an example of a reaction mechanism for this reaction right here. We could have the first step where two nitrogen dioxide molecules actually encounter one another, and they're going to exchange an oxygen to produce nitrogen monoxide plus nitrogen trioxide. And all of these are in the gas phase. I'm leaving off the gas just because all of our reaction mechanisms that we're going to investigate for the first little bit here are gas phase. Of course, that's not the products we're looking for. So there is a second step, and that is that nitrogen trioxide is then going to encounter the carbon monoxide and exchange an oxygen to make nitrogen dioxide and the carbon dioxide. And that is the proposed reaction mechanism. Now, I could, if I had sufficient creativity and time, I could probably come up with 100 different possible ways that this could proceed that are sort of logical and consistent, and I'm not making atoms appear out of nowhere or disappear into nothingness, that everything adds up, as it were. And so just because someone has presented a proposed reaction mechanism doesn't mean it's true. And we need to have some tools to figure out whether a reaction mechanism is valid or invalid, so we can immediately throw it out if it's invalid in some way. And then if it's valid, can we find some evidence to support it and give it evidence? We'll never be able to prove a reaction mechanism outright because we can't actually watch the molecules in action. But we can build a very strong case for a reaction mechanism if we're careful to think about the consequences and the evidences that we can find for that mechanism. So the first thing we need to do to validate this mechanism is to see, does it even add up to the total overall reaction? So to do that, I'm going to just kind of add these two reactions together like we've done before with Hess's law in 1210, for example, I'm going to put all of the reactants on the left side, and that is the reactants from both steps. So we'll have NO2 and NO2 and NO3 and CO. And then I'll put all of the products from both steps on the right side. So we have NO and NO3 and NO2 and CO2. Now this certainly does not look like our reaction yet, but we can now do some cancellations. I have NO3 on the left side and the right side, so let's cancel that out. And I have NO2, I've got one NO2 here and two NO2s there. So let's get rid of one of them. And what we're left with is NO2 plus CO yields NO plus CO2, which is indeed the reaction, the overall reaction that we're looking for. So this reaction mechanism passes that first hurdle about whether it's even a valid proposal or not. Now that we know that it is a valid proposal, let's look at it a little bit closer. And what we see is that there's one species here that doesn't appear in the overall reaction at all, and that is NO3. NO3 is generated in the first step, and then it is consumed in the second step so that it doesn't appear in the overall reaction at all. NO3 is what we call an intermediate. So many reaction mechanisms will have one or more intermediates. Intermediates are often very short-lived, and that would make it difficult to observe them directly. But you can observe them directly in some cases, and that would be one point in the favor of a reaction mechanism. If I could run this reaction and maybe spectroscopically or through some sort of a chemical reaction, observe that NO3 is indeed present in my reaction chamber, then that would be a point in favor of this reaction mechanism. So you can identify intermediates because they don't appear in the overall equation, and they are first produced and then consumed. In the next section, we'll deal with another category where they don't appear in the overall equation. They are first consumed and then regenerated. So you need to be careful. An intermediate is first produced and then it is later consumed. An intermediate is not the same thing as a transition state. So remember in our reaction coordinate diagrams, I'll just draw one real quick, a real sloppy one. You know, up here you have the transition state, which is kind of like a new chemical compound in that it is forming new bonds and not quite yet done breaking the old bonds. So you could argue that it's sort of a new species where everything is kind of half bonded together. But really importantly, if we think of the energetics, that transition state is unstable. It's at that maximum point in energy, and it will spontaneously either continue over to the product side or will return to the reactant side. It cannot remain up there. Just like if you had a bowling ball and you tried to balance it on the head of a pencil, if that pencil were actually perfectly sharp and the bowling ball were actually perfectly round, then you couldn't do it. If nothing else, quantum mechanical fluctuations might cause that bowling ball to begin to tip, and once it is infinitesimally off perfect center, then it will roll off to that side. Well, transition states are the same way. They cannot remain there. They will go one way or the other. An intermediate is at least metastable, and we'll show you what that means in terms of a reaction coordinate diagram. It will not be at a local maximum. And so nitrogen trioxide, it does exist stably in the world. I could make some nitrogen trioxide, and as long as there isn't any carbon monoxide around to consume it, perhaps I could store it and study it. It's an actual chemical compound. And so that is an intermediate. Reaction intermediates are important. Oftentimes they're either so dilute or so short-lived, however, that we cannot observe them directly. So let's look at, I've been talking about reaction coordinate diagrams. Let's look at a reaction coordinate diagram. There we are. For a two-step mechanism. This is sort of generic, right? It could apply to the mechanism that I just showed you. So on the left here you have the reactants, and there will be some activation energy required to reach that first transition state, and then it will settle down into intermediates. So each bump on the reaction coordinate diagram is going to involve a transition state, some reactants, and some products to that step. In this case, let me hold up, sorry. I'm going to get my mouse to act like a pen. If I can, my laptop's struggling. There we go. Mouse pointer as pen. Okay, so here we would have something like 2 NO2s. That's the ugliest 2 in the world. That's what you get when I'm trying to draw with a touchpad. Oh my goodness. 2NO2. Okay, and then that transition state is going to be where the oxygen is only halfway through the process of transferring. Here we would have NO plus NO3. NO3. There we go. I've learned if I click on the left side of my button, then it doesn't read it as a right click instead of a left click. All right. And then for the second step, we'll have that NO3 plus carbon monoxide and that is going to involve the transfer of the oxygen from the nitrogen trioxide to the carbon monoxide, and that will result in our products of carbon dioxide, CO2 plus NO2. Right, so this reaction coordinate diagram could be representative of the mechanism that we just saw. And of course there are all the same sorts of ideas. Step 1 is going to have its own activation energy. Looks like that. That's the activation energy for step 1. Step 2 would have, Step 2 would have its activation energy. In this case, that's shown to be much smaller. Of course, the second step could have a higher activation energy or a lower activation energy. That depends on the particulars of the reaction. And then if we could compare our product and reactant energy directly, then this here would be the delta H, or the enthalpy of the reaction. So it looks like we're looking at a slightly endothermic reaction with 2 steps, and the activation energy of that first step is larger than the activation energy of the second step. And that really prepares us to talk about the next really important part of reaction mechanisms. Each individual step has its own activation energy. It can be thought of as its own little reaction. So let's get rid of this. And that means it can have its own rate law. So let's erase that. There we are. So the rate law for the first step and for the second step, they're their own little reactions. They each have their own rate law. So what would be the rate for the first step? Well, we can't do initial rate method or integrated rate law methods to determine the rate law experimentally for only one part of an overall reaction. But what we can do is look at how this reaction proceeds, and because it is an elementary step, the rate law will actually depend only on the stoichiometry of the reactants. And so there are different types of elementary steps. There are elementary steps that we call unimolecular. They would be in the form of like A goes to products. And there are elementary steps that are bimolecular. They would be in the form of A plus B goes to products, or A plus A goes to products. So unimolecular elementary steps involve the spontaneous decomposition of a larger molecule. Bimolecular steps involve the encounter between two molecules. They might be different molecules, they might be molecules of the same type, doesn't matter. And for unimolecular molecules, the rate is going to equal the rate constant times your reactant. For bimolecular elementary steps, it's going to be rate is equal to K times AB, or K times A squared if they're the same. So the rate law in this case just depends on what your reactants are. You might say, do we have other levels of molecularity? Do we have trimolecular elementary steps? And the answer is kind of. So there are some very special, exotic examples of where you see a trimolecular elementary step. Generally speaking, the probability of having three molecules simultaneously collide and come together is vanishingly small. Think about these steps are not just a matter of these two chemicals reacting with each other, but we're talking about actual encounters between molecules. And whether it's gas phase or aqueous phase, in either case, there's vast distances between the reactants. And having one reactant encounter the other, well, that will happen from time to time as they move around in space. But having three of them come together at the exact same point in three-dimensional space and the exact same time with a very short window of encounter, it's extremely unlikely. And so we're only going to deal with unimolecular and bimolecular reaction elementary steps. So, so if those are the forms of the rate laws, then we can talk about the rates for each of these two steps. So rate 1 is going to equal K1. It has its own rate constant times NO2 squared. And rate 2 is going to equal K2 times the concentration of NO3 and the concentration of carbon monoxide. And those are the two rate laws. Now, the overall rate of this reaction will follow its own rate law. And based on the reaction mechanism, we can determine what rate law would be predicted by this mechanism. So let's think about it. If you have a multi-step process and each of them has their own rate, what is the rate of the overall process? And the answer is pretty simple and obvious. The rate of the overall process is going to be equal to the rate of the slowest step within the mechanism. And a good example of that is the process of boarding a plane to go travel somewhere. There are lots of things that you need to consider, like how long does it take to park your car and walk to the airport? How long does it take to check your bags and check in with your ticket? How long does it take to actually walk through the terminal? How long does it take to find your seat? All of these are relatively fast, and anyone that's traveled knows that the slowest step is how long does it take to get through the TSA security line. And if you're wondering, how early should I arrive at the airport? How long does this process take? You can pretty much just ask the question, how long does it take to get through security? And that's going to be the answer to how early you need to arrive. And so one of these steps is going to be faster than the other. And it doesn't matter if it's 10 times faster or 100 times faster. There tends to be big enough differences in the rates here that we can just call one step slow and one step fast. And in this case, this proposed reaction mechanism, the first step is the slow step. And here I want to come back to our reaction coordinate diagram. That first step has a much larger energy of activation, and so you would expect that the first step is slower. Or if we're doing the reverse, if I give you a reaction mechanism where the first step is slow and ask you to draw the energy coordinate diagram, then you better draw that first step as having a larger energy of activation. Okay, so if this first step is slow, then what is the rate of the reaction overall? Well, the fast step doesn't matter. Only the slow step matters. So the rate is going to equal K1 times NO2 squared. And that's what this reaction mechanism predicts. Now you can do initial rate method or integrated rate law method to experimentally determine the reaction order with respect to NO2 and carbon monoxide for this reaction. Suppose you carry out those experiments and you find an experimental rate law that doesn't match what this reaction mechanism predicts. Well, then you can throw it out. You can say that was a fine story that you told about how this reaction proceeds, but it's wrong, it's false, and I've proven it because the observed rate law does not match the rate law that would be dictated by this reaction mechanism. Okay, let's think about it the other way. Suppose you carry out those experiments and you do find that this reaction is 0th order with respect to carbon monoxide, 2nd order with respect to nitrogen dioxide, and so its overall rate law matches what this mechanism predicts. Does that prove that this mechanism is accurate? No, not quite. Again, with sufficient time and creativity, I could come up with lots of different really fabulously complex mechanisms, and at least some of them would also predict this rate law. And so having experimental confirmation of the rate law is at best some additional supporting evidence in favor of a particular reaction mechanism, but it is not proof. I feel like I'm in a court of law here. What you want to do is identify the rate limiting step, the slow step, and you can have 3, 4, 5 steps in a reaction mechanism, but one of them will always be the slowest step. That is the rate limiting step or the rate determining step. And its rate law will be the rate law of the reaction overall. Okay, now sometimes you're going to run into more complex mechanisms. So let me just erase this. We will start all over with a new reaction. Okay, so let's consider this overall reaction. 2NO plus Cl2, that is going to form 2NoCl2. Sorry, 2NoCl. All right, we have an observed rate law here. The rate is equal to K times NO cubed times Cl2. I'm sorry, that's NO squared. Okay, NO squared Cl2. And so that rate law, you might naively say, well, that's consistent with a termolecular single-step mechanism. All three molecules come together and they break and form bonds, and you get your NoCl out the other side. But you know better now. You know that the probability of having a termolecular elementary step in your reaction mechanism is vanishingly small. So there must be some other complexity that's going on right now. But we still have a third order reaction overall. So there is no single elementary step that's going to lead to this rate law. Well, here's how we solve this problem. Here's a proposed mechanism. NO plus Cl2 is in equilibrium with NoCl2. And this will be the fast step. Equilibrium reaction that is fast. And so we'll establish equilibrium here. We'll have an equilibrium constant K that is going to dictate the concentration conditions of this equilibrium reaction. And then the second step says NoCl2 plus NO is going to form 2NoCl. So this step, you just transfer one chlorine atom from one to the other, and this is the slow step. Okay, so each of these elementary steps is now bimolecular or unimolecular. We'll have a bimolecular elementary step going forward, a unimolecular elementary step going in reverse, and a bimolecular elementary step going forward. Let's consider the rates of each of those three steps. I'll write my rate constants here. We have a K1 and a K negative 1 and a K2. Each of these has its own rate constant. And rate 1 is going to equal K1 times the concentration of NO times the concentration of Cl2. And rate negative 1 is going to equal K negative 1 times the concentration of NoCl2. And finally, rate 2 is going to equal K2 times the concentration of NoCl2 times the concentration of NO. And this is the slow step, so this is the overall rate. However, the rate law that we observe does not match this. And why is that? Well, because NoCl2 is an intermediate. It's an intermediate. We can't easily observe it or measure it. We don't even know what its concentration is. And so how could we do an experimental way of finding the rate law using something that we can't even measure? Well, let's look closer at this equilibrium first step. If it reaches equilibrium, then that means that the rate going this direction and the rate going this direction will be equal to each other. That's what equilibrium means, that there's not going to be any more changes in the concentrations because they've established that equilibrium. And so that means that rate 1 is equal to rate -1. And here we have rate 1. So K1 times the concentration of NO times the concentration of Cl2. And here we have rate -1. Rate -1 is K -1 times the concentration of NoCl2. Well, we can take this equality here and we can solve for our intermediate concentration. So NoCl2, we cannot experimentally observe its concentration, but thankfully, because of the definition of equilibrium, the fact that these rates must be equal to each other, we can calculate it. So NoCl2 is going to be K1 over K -1 times the concentration of NO times the concentration of Cl2. And now we can take this quantity and put it into that rate law there. And I'm running out of room, so I'll write it up here, and then we'll talk a little bit about it. So rate 2 is going to equal K2 K1 over K -1 times NO Cl2, and then here's the other NO. And now this K2, K1 over K -1, those are all constants, and so we can change them to just be the K observed. The observed overall rate constant is just the combination of K1, K2, and K -1 in this way. And then we'll have NO squared, there's 2 of them, and Cl2. Well, now look at this. That rate law does match what we observe. And so this third order overall rate law is actually predicted and explained by this sort of a mechanism. We'll see these mechanisms frequently where there is an equilibrium on one or the other steps. And your slow step is going to involve an intermediate in its rate law. And so we solve for the intermediate concentration using the equilibrium condition, that the forward and reverse rates in that equilibrium step must be equal to each other. So that's all pretty common. Now, there's one cool little thing that your book does not cover, and so you don't need to know it for the purposes of the exam or anything else. I'm only going to spend 30 seconds on it, okay? We can take this equality right here and we can rearrange it. If I have NoCl2 divided by NoCl2, what does that equal? That would be K1 over K -1, right? But what does that also equal to? The concentration of the products divided by the concentration of the reactants, each raised to the power of their stoichiometric coefficients in the equation. Well, that is equal to the equilibrium constant. So there is just one quick connection between the equilibrium constant and the reaction mechanism itself and the individual rate laws that make up that reaction mechanism. And this is, I think, really significant because most of the time thermodynamics, which governs your K equilibrium, is disconnected from kinetics, the reaction rate. For example, some equilibrium is reached quickly, some reactions reach equilibrium slowly. It doesn't matter, the equilibrium condition is going to be the same, whether the reaction happens rapidly or slowly. But here is actually one connection between kinetics, the rates of reactions, and thermodynamics in the form of the equilibrium constant. Okay, so do you want to do one more example? Of course you do. That's why you took this class. So let's do one more example here. Sorry, it looks so similar, I had to make sure it was in fact a new example. So here we have 2 NO gas plus O2 gas. That's going to form 2 NO2 gas. And we can observe two things about this reaction experimentally. We can observe that the delta H of reaction is equal to negative 116.2 kilojoules per mole. And we can observe the rate law, that the overall observed rate law is equal to K NO squared O2. So a proposed mechanism is that we have NO plus O2 in equilibrium with NO3, and this equilibrium is the fast step. And so we will achieve equilibrium because that reaction elementary step is fast. And then the second step is the NO plus NO3 forms 2 NO2, and this is slow. So first of all, let's check, is this reaction overall a valid one? Does it add up to give us the overall reaction? On the left side we would have NO plus O2, which is what we have here, plus an NO3. On the product side we would have 2 NO2s, which is what we have over here, plus an NO3. That extra NO3 cancels out because it appears on both sides, and these two steps do indeed add up to our overall reaction here. And then what is going to be the predicted rate law based on this mechanism? Well, let's look at the slow step. It would be rate is equal to K2 times concentration of NO times the concentration of NO3. Only NO3 is an intermediate, and so we don't know its concentration and we can't measure it. Thankfully, NO3 is a part of an equilibrium in the first step. So I know that the forward rate of this first step will be equal to the reverse rate, and the forward rate is K1 times the concentration of NO times the concentration of O2. That's equal to the reverse rate, which is K negative 1 times the concentration of NO3. And we can rearrange this to get an NO3 concentration equal to K1 over K negative 1 times NO O2. When we put this into the overall rate law predicted by this mechanism, then we get the rate is equal to K2, K1 over K negative 1 times the concentration of NO times the concentration of NO times the concentration of O2. And we can simplify this to just be K observed. So our observed rate constant is equal to K2 times K1 divided by K negative 1. And we would have NO2, we would have NO squared O2, which is indeed the observed rate constant. And so this mechanism is plausible. And if I were to draw a reaction coordinate diagram I can actually be fairly detailed in what I draw. So first of all, the overall reaction is exothermic. So I'll put my reactants higher than my products. I know it's a two-step mechanism, and the first step is fast. So I'll have a small hump for the first step and a taller hump for the second step. There we are. And because this first step is an equilibrium reaction, in particular, I should probably put these reaction intermediates not too far removed from the energy of the reactants themselves. So this reverse activation energy is not too terribly different than the forward activation energy. That is what tends to lead toward equilibrium reactions. And so, this isn't perfect. Should those intermediates be higher in energy or lower in energy? I'm not sure. I don't have quite enough information to make this perfect reaction mechanism, reaction coordinate diagram for this reaction mechanism. But I can add really a fair amount of detail. We're done looking at particular examples. We're only going to look at the simplest things like these pre-equilibrium mechanisms. And I want to point out that reaction mechanisms can be really complex. They can have really exciting, interesting concepts that you'll explore later if you go on to take Chemistry 3610 and 3620. And two of those ideas I'll just introduce really briefly is collisional activation. And so some reactions will require a reactant to sort of build up enough kinetic energy by colliding. And those are interesting because it doesn't matter what it collides with. It's just a collision with any other gas particle is going to have a certain probability of activating it vibrationally and transferring the right amount of energy. And so having collisional activation means that your reaction mechanism and your rate law are going to have like this generic anonymous species, and it can collide with anything at all for that step. And then another interesting idea is what's called the harpoon mechanism. This is where an electron will jump from one reactant to the other. And basically it means that they don't have to actually collide, they just have to get close enough for that electron to move. And then once the electron has moved, well, this one is negatively charged and this one is positively charged, and that will draw them in together. So these are reactions where you get rate constants and you get what we call a collisional cross-section, or sort of like a description of how likely two things are to collide. You get numbers that are just really nonsensical, and that's because they don't have to actually collide. If they just get close enough, then the electron will jump over. That will cause an ionic attraction that then pulls it in. It really is almost like a harpoon. One reactant is harpooning the other and drawing it in. So this can get really fun as things get more complicated, but I'll just leave it at there.